All right. So today we're going to finish up chapter 16, which when we see what you're doing, you're going to be like, oh, totally obvious. Because it's pretty much what we were doing, just now dealing with solids rather than acids and bases. So the mastering homework on Friday is a little bit of review plus this stuff. So the group quiz on Friday, same thing, a little bit of review plus this stuff. And when you see this, it is kind of a review when we do the solubility salt. And the exams are taking me way longer to grade than I thought they would, so they'll be back on Friday. I mean, if you set up the problem correctly, you usually do fine. If the question is, let's say you were looking at this one. Right, so the question is, find the KB of a base, oh, what's the other thing that was in here? A concentration 0.5 or something like that, right? So what should be the two ingredients that are the reactants? A base and, okay, so that was like the majority of the problems, right? So it should be base and water. Makes them what? HB, and then what's left over? OH minus. Alright, so I gave you the pH. So how do I get from pH to a value that I can plug in here? Oh no, they'll give me the H pluses. There are no H pluses. You have to subtract from 14, and then that's the POH, which is then the P. This just goes here. Right? So that's why this is a 15-point question, because there's a lot of little tricky bits to it, right? So I gave it pH, but it was a base, then you had to have the OH concentration. It was a 15. Yeah. Alright, that's 12 maybe? 12? It was definitely more than 10. Because I knew that there was going to be a trick to it, so there was like 2 5-pointers, 2 12-pointers, and 2 15s. And the reason it was so many points is that I figured most people would screw this part up. That way you get at least half credit for starting whatever you did. So that's why it took me a long time to grade this, the partial credit. Because if you don't set the problem right, then I have to figure out, well, assuming you set up it wrong, did you then do the math correctly based on your wrong assumptions? It's very tedious. It would be a miracle. First of all, it would be a miracle. They do. If somehow you made so many errors that you get the right answer in the end, I would probably take off very few points, I guess. Yeah. Like, I have a little rubric set up, so like, if it's a 10-point question, like, you get 2 points for setting up the problem right. You get 2 points for assuming you set the problem incorrectly, like regardless of how you set it up, did you then plug in the chart correctly? Alright, then based on plugging in the chart, did you then set the Ka, Kb equation correctly? You only get penalized once. Yeah. Which is why it takes me so long to grade it. So I'm like, okay, you did a bad equation, but then did all your math work out based on your bad equation? Because I don't want to be double jeopardy. Like, I don't want to penalize you multiple times for making one error at the beginning. So if you make an error at the beginning, I then follow your math and see if your math is reasonable. But yeah, I try. So, on that topic, let's talk about solubility products. Alright, so precipitation reactions are reactions in which one, and this, yeah, just one. One of the products, I'll say one or more. One or more of the products are water soluble. Alright, we have done this before. We just didn't column this maybe. Alright, so if I have Right, if I had sodium hydroxide and I mixed it up with some silver chloride, how could I figure out what the two products were going to be? Right, they swap partners. Right, we do the little do-si-do thing, right? It's now the sodium goes with the chloride, and the silver goes with the hydroxide. Right, that sounds vaguely familiar. And that one's the aqueous, and this one's solid. Definitely do this in 108. Talk about a little bit this semester, right? I put in 2 aqueuses, I get out an aqueous and it's soluble. There's that table of solubility products somewhere in your book or in your notes that you could go back and look at. If you can't remember how you know what's predictable. Table 4.1 in your book. You're looking for it. Yeah, welcome. Try me handy. Now we're going to take these solubility predictions, right? What we just said up here is we predict that silver hydroxide will be a solid and sodium chloride will be a aqueous. We're going to take that prediction. And predict how much solid can be made. I mean, if you don't know them already, you might want to just go back and review them. We're going to use the same ones over and over again. Like, it's usually everything's going to be silver, or I use a lot of silver. What else do I use? Oh, that's silver again. I use a lot of sodium, so that's always soluble. Silver is always insoluble. So, alright, so if I wanted to figure out how likely this reaction is to go to products, what letter of the alphabet should I use to talk about its likelihood to go, in this case, to the product? Big K. This is KST, the solubility product constant. Sure. Alright, so now we're using big K, right? Big K tells me products of a reactant at equilibrium reflects the solubility of a compound, and in your textbook specifically it's called the solubility product constant. Alright, so let's say for example, I'm going to start with the silver bromide solid, and I'm interested in what 2 ions it will turn into in solution. What charges should they each have? Alright, that should be familiar. Alright, so far so good. Let's say I want to write my solubility product constant equation for this. What goes on top? Product or reactant? Products. Okay, so I'm going to have my silver, 1, and my bromide -1. What goes on the bottom? Just 1, right? Because it's a solid. Where am I at in my reaction if I'm using the K? I'm at equilibrium. So these up here are the equilibrium concentrations. If they are the equilibrium concentrations, will any more solid dissolve at this point? No, right? You're at the maximum amount of products being made. Alright, so you're at equilibrium. Max amount of solid dissolved. What do we call that solution if we are at the point where no more solid will dissolve? Pressing S. Saturated. So the KSP is a measure of how much solid you have to dissolve to get to the point of a saturated solution. Oh, okay. Concentrations. They're going to be in molarities. Alright, because big K is always in molarities. So for your mastering, I made sure all the KSPs are in every question. But if I somehow missed one, they are in Appendix 2 at the back of your book. Pretty sure I call all of them. That's pretty nice. Sometimes on accident, but usually on purpose. Alright, so what does this KSP tell us about concentrations in solution? How can we use it? How do we calculate with it? I thought maybe I was going too fast. Alright, so KSP is measured by doing experiments in the lab and determining concentrations of ions in solution, right, just like we did all the other big Ks. They're all experimentally determined. Little Ks, experimentally determined. Okay. Let's do an example problem. Alright, let's say I have no, let me do this other problem first. Sorry. We'll work up that one. So determine the solubility. Alright, first of all, let's talk about this KSP. How relatively big is this KSP? It's super tiny, so how much should it dissolve? Almost nothing. So this is considered insoluble in general, but we're going to calculate how many ions does it possibly make given this tiny, tiny, tiny KSP. So if I want to use the KSP equation, what do I first need to do? What's my chemical reaction going to be? Just like we did for the other one, it's going to be alright, that's just something to flesh out. If I need to use the KSP, what concentrations do I need to find? The something concentration. Equilibrium concentrations. How do I find equilibrium concentrations? Ice chart. Alright, what do I do about the solid? It's like water. Yep, anytime you have a pure solid or a pure liquid, just draw an arrow down. It doesn't change. Alright, at the very beginning of my experiment, how many ions exist? Right when I drop it in. We consider that 0. Okay. How many X's should each of these get? Yep, that's 1. So at equilibrium, looks like that. So if my KSP is now equal to what times what? X squared, right? Let's write it down. What unit should this be in? Big M. So, I would expect that molarity of silver ions in solution when I put silver iodide in there. Water. Yeah, I'm just saying, like, I have a rock of silver iodide, I drop it in a beaker of water, I would expect that molarity of ions to show up. Alright, so it seems super easy. It is. It's way easier than anything we did in chapter 16. Right? What if... Ooh, okay. Okay, we're not ready for that one yet. Let's do this one. What if I now have... Alright, so these are typically how these questions are written. Calculate the molar solubility of, in this case, lead fluoride in water given the KSP is 1.17 times 10 to the negative third. So what are they looking for? Are they looking for the KSP? Right, because it's given. Definitely not. What's the only other thing you could be possibly looking for? X. So you're looking for the equilibrium concentration of the ions. So this phrase right here, molar solubility, means find the equilibrium concentration of the ions. Right. And if it's molar solubility, what units does it need to end up in? Molarity. It'll let you know if it wants to be anything but molarity. It'll ask for it in, like, sometimes they ask for it like in grams per liter. The majority of the time, just molarity time. Alright, so what should be my single reactant in this chemical equation? Okay. No, because it's not reacting with the water. It's just dissolving in the water. So it's doing a physical change, not a chemical change. Alright, how do we know what charges these things have? Right, there's ions now. I mean, we don't have a good rule for lead, but what's fluoride's charge all the time, always? Minus. Okay, I have 2 fluorines, so what should the lead charge be? Alright, so now if we set up our ice chart, again, we start with 0, but now what value of X does the lead get? Okay, 1. What happens to fluoride? Plus 2. So now, what is wrong with how I've written my KSP equation? I need to square it. So you're going to get KSP equals x times 2x squared. So that's x times 4x. Alright, so if you have your calculator out, go ahead and fish it out because we're going to have to figure out how to do a cube root. Cube root. Just about everybody's calculator should have a button for it. Yeah. So now we have 1.17 times 10 to the negative third equals 4x cubed. Alright, what do I do first? What's the thing I should do first before I cube root it? Divide by 4, okay? Let's see what it's down. Should be 2.93. Let's see. Next fourth. Now at this point, cube root. So on your calculator, either you're going to have a button that is like a square root sign but has an X, or you could raise it, use the caret, and raise it to the 1/3. You'll get the same answer either way, just depends on what's easier for you to do. Yeah, on mine, you press 3. Well, which way do I flip it? Oh, there we go. 3. That, and I punch in the number 2.93. Or I probably need to click on something. Yeah, so if you have one of these type of calculators, where we go? Oh, there we go. 3, inverse caret, parentheses, type in the number I want, 2.93, negative 4. It'll take a second for it to think about it because cube roots are tricky even for calculators. You'll get the answer like that. Or you could do 2.93, negative 4, to the caret, 1/3 with a lot of parentheses. You'll get the same answer. Questions? Oh, so I have it in scientific. So if you press the second button and the degrees thing, the standard is flow, and it means you want it as a decimal point. Scientific always gives it to you in scientific notation. I prefer the scientific notation. Only because I end up counting across all the zeros. I end up messing up. Flow. Yeah. Flow means give me it as a decimal. Scientific means scientific notation. Engineering is kind of wacky. I don't like the engineering setting. Probably why I'm not an engineer. Alright, so which concentration is this referred to? Lead. How do I find the chlorine concentration? Multiply by 2. So this is just for the lead 2 plus. I would multiply it by 2. What is that? Right, so twice as many chlorines in the solution as the lead. Right, that makes sense. You just have to read to see which one they're asking about. Feeling confident in that way? Mm-hmm. That's fine. Either way, scientific, not scientific, as long as the right digits. Alright. What do I have next? This is where we get tricky. Alright, so solubility and the common ion. So what if you had a test tube of saturated silver nitrate and I, personally, added more potassium nitrate to your test tube? Okay, so I'm saying this, right? If I add more potassium nitrate, what concentration is it going to increase? Right? This is going to cause increase this concentration. So what will happen to my reaction? It's going to shift back towards reactant. Alright, so that's stuff we know, right? We add more of this, it's going to cause it to shift. Alright, so the process of adding more of one ion is called the common ion effect. And does it increase or decrease the concentration of solid in solution? It increases this, right? I have more solids, so what happens to the concentration of the ions? They decrease, okay? And we can predict by how much they will decrease. So let's go ahead and do that. KSP is a constant. It's going to be the same. But the concentrations will get lower. Yep. So, let's say, for example, does everybody have this? Okay. That's not what I mean. I want to find the molar solubility. That's a very good question. Alright, find the molar solubility of silver thiocyanide. If I just have it by itself in water, case 1, and case 2, I have a competing ion. Alright, so let's do... Given that KSP is 1 times 10 to the negative 12. Alright, so let's say I'm just in water. Alright, so if you're given that equation, you're going to need an ice chart, right? You're going to be tempted to not write out the ice chart because it seems like KSP is always equal to x squared. I'm going to guarantee the time you choose not to write the ice chart is the one where it's like a double, and you forgot the double and square, and then you're in trouble. So, take 2 seconds and just, even if you don't write the whole chart, make sure you write the equation so you can see if anybody's double or triple somebody else. Alright, now KSP 10 to the negative 12 equals x squared. So x is what? 1 times 10 to the negative 6. Alright, just standard, those are the concentrations of each, no problem. Alright, so then, let's see what happens when I add in some sodium thiocyanate. Were there any questions on this one? Now, in part 2, I'm saying I have this. Alright, so now I have 0.1 molar sodium thiocyanate also in my solution. Where do I put that information? Did I add any more silver to the solution? No, right? So that's still 0. What is now the initial concentration of thiocyanate? Okay, 0.010. Alright, so then we're still going to have, they're each equal to 1x. You don't worry about it because it's not competing with anybody else. It would be on both sides and then canceling out. Yep, still just a spectator, hanging out. Alright, so now I have Alright, does anyone see what the issue is going to be here? It's going to be a quadratic. Let's look at this x I'm adding to it. What are the chances that this x I'm adding to it based on my KSP is going to be in the ballpark of 0.01? Pretty small chance. Let's solve for x. If it's close, then we'll have to go back and do the quadratic. If it's not close, then we'll make it say that was a good assumption. Alright, so can I assume both x's are small? No, right? That's catastrophe. Okay, so to make our life easier, we're going to assume that x is small, solve for x, and see if that was a good assumption. What do I know to use to compare it to? What is a good assumption? How do I figure that out? Same 5%. Alright, so now I'm left with 1.0 times 10 to the negative 12 equals 0.010x. Was that a good assumption? Pretty gosh darn good assumption. Yeah. They're not even in the same range, right? So negative 10 to negative second, not close enough to each other at all. Alright, so the question is, what happens to that value of x? When I didn't have any common ion, it was negative 6. Now I have common ions to negative 10. What happened? Did it increase or decrease? It decreased, right? The amount of silver in solution decreased a lot, right? 4 orders of magnitude. What must have happened to this then? What happened to my amount of solid? It increased, right? If this decreased, this must have increased, right? So less solid dissolved. Alright, so molar solubility decreased. which means you can think about it either way. The amount of solid increased or less solid dissolved, whichever one is conceptually easier for you to think about. I like to think about less solid dissolved. Either way. What was the percent ionization? It was a similar concept. Yep. Yeah, we'll probably do it on Friday. When I hand back the test, you have them in front of you. Because I don't actually remember the question off the top of my head. But yeah, something like that. Like percent ion. It is actually the same exact concept. It's the exact same thing, except in this different. This is the shot lead. Yep. Yeah, so I mean, that's why I'm saying like this little section of the chapter is what you did before. It's just now using a solid instead of an acid base. Exact same kind of thing. Alright, so what are some important things about common ions we have to worry about? 1, the solubility of a salt will always be reduced when you have a common ion. And by that I mean the value of x, right? Whatever x you're solving for will always decrease. There'll always be less ions in solution when there's a common ion. And this is the approximation we just made, right? That the amount of common ion added is way bigger than the ions that we throw free in solution. So if you get to the point where you're not sure if that was a good assumption, it's the same 5% rule to see if that was a good assumption or not. Alright, so the last section of this stuff, I'll wait till everybody has that written down. I'll slide it up. How do we know? We're going to compare Q and K, just like we've done a bunch of other times. How do we know when a precipitate will form? Well, are we at equilibrium? Are we not at equilibrium? On what side of equilibrium are we? And what do we have to do to get to equilibrium so we get to a saturated solution? Fascinating question. I can tell you guys are all very excited about this. Good? Pretty good? Alright. Right, so how do we know when precipitate will form? We're going to compare Q and KSP. And see on which side of the reaction we are. So, let's say I have this reaction. I use a lot of silver. Good ion. Alright, so let's say I have that reaction. If I wanted to write the Q equation, what is Q equal to? And silver. Right. Let's say my value of Q equals my value of KSP. Where am I in my reaction? I'm at equilibrium. What would I call this solution then? Starts with an S. Saturated. let's say we're at the point where Q is less than K. Let's see. Which direction is my reaction needing to go? So it's going to go to the right. Alright, so if my Q value, oh, sorry, I'm thinking two different people one time. Makes more product. I was going to say use up, anyway. So if my Q value is less than my KSP, this should be much easier to think about because there's no fractions now. K and QSP are just single values with no fractions, right? The bottom is always 1. And so you just legitimately need to get a bigger number. So to get a bigger number, you need more product. That's all there is to it. Alright, more product. So what's going to happen to my solid? Will it dissolve more or dissolve less to make more product? More, right? You expect the solid to dissolve more. It is supersaturated, so I would call this one unsaturated. This one's saturated, this is unsaturated, and this last one is supersaturated. Means you have added so much solid to the solution that there's stuff on the bottom. It'll just start to collect whatever your Kool-Aid mix or your sugar packet. Right, you've added so much sugar to your coffee that there's just like the sugar scum at the bottom when you're finished drinking it. Okay. So these are the same, right, same directions we had before. So now let's snap your names. Alright, let's do one last example problem, and then we'll be done for today. Which one should I choose? Ah, okay, this one's good. Alright, I'm ready. Alright, this is the last thing in chapter 16. Alright. Oh gosh, these are both good. Alright, so you have a solution. I was going to do more than one, but now I don't have very much time, so. Yep. Alright, so let's say you have a solution containing lead nitrate and sodium bromide. The form a solution. The question is, what is Q, what is KSP, and where are we at? How are they, like Q, are they equal interrelationship? Yes. Alright, so this combines everything we've just done into like one super problem. Alright, so I have two things in solution, right? So I'm saying I'm at the point where I have PbNO3, that's an aqueous, squishy, and a sodium bromide. What will be one of the products that we will make? Okay, the Pb goes with Br. Okay, what's the charge for Br always, all the time? -1. In this case, what's the lead equal to? +2. So how do I solve that? Little 2, okay? What's your guess on if that's a solid or an aqueous? It's a solid, right? It has lead. Lead's always a solid. That's good, just rule of thumb. Silver's lead, always solid. Alright, what do I have left to make then? Okay, sodium. Alright, the sodium's always a +1. The nitrate's always a -1. Is my equation balanced? No. What do I need to do to balance it? If I do a 2 here, then where else do I need 2? Over there. And this one's aqueous, pretty much because it's always a sodium. Sodiums are always aqueous. Alright, good. That's like review from like 108, sort of, right? Like, okay. If I'm concerned about solubility, what are the only things in this reaction that I am concerned about solubility? If it only deals with solids, solubility is of a solid, what is the only thing I have to worry about? Okay. Everything else is just hanging out in solution, spectating, not doing anything. Alright, so do you want to do Q first or KSP? Q? Okay. If I do Q first, do I do an ice chart in order to find Q? No, right? Because Q is anywhere but equilibrium. So I just plug in the values that I have up here. Right, because if I solve it at equilibrium, then I'm actually solving for KSP. So I want to find Q. So Q is the initial amount. What should Q be equal to? Okay, Pb2+. And what do I do about this bromine? Alright, so how do I figure out what the lead concentration should be? Any guesses on what the lead concentration? There's two options. Is it number 1 or number 2? Okay. Alright, so then where do I get the bromine concentration from? Number 1 and number 2? That's Q. Yep. Alright, real quick so I can finish this up. If I want to find KSP, I use the same equation I had up here. Let's see what's that, 0.05. 0. Alright, I'm starting to rush. So what I'll do is we'll stop. We'll finish the problem Friday. You can certainly finish on your own. This will be the very last thing. Bring your chapter 17 notes on Friday, and we'll start thermodynamics. Entropy, enthalpy, Gibbs free energy.